Okay, so today we'll continue again with our unit number 1, which is Introduction to Engineering Risk and Uncertainty and Risk Methods. So the first topic we've already discussed. Now the second one is Introduction to Engineering Uncertainty Modeling. So a central role for engineers is to provide basis for decision making in regard or in relative to the cost efficient safeguarding of personnel, environment and assets in situations where uncertainties are at hand. So the main role of any engineer in the case of uncertainty or in the case of decision making, it is basically related to the cost efficient safeguarding, that is protecting the personnel, that is our personal property or assets, environmental assets and assets in situations where uncertainties are at hand. So a classic example that I have cited here is the decision problem of choosing the height of a dike. So we know what is a dike. This is a dike and somewhat flooding occurs if the dike's height is short. So if the height is short, flood will take place. But if we increase the height of a dike, the flood cases are lessened. So here the example for decision, like in a problem of a dike, how you can do or how you can decide on the problem. We'll discuss that. So the rise of dike flooding can be reduced, as I mentioned, by increasing the height of the dike. However, due to the inherent natural variability in the water level, a certain probability of dike flooding in a given reference period will always remain. So different rivers or different free flowing flows have different water level. So obviously if the water levels are different, their variability or the probability of even flooding is also different, but the reference period, that is the period of the flood, will always remain the same. So risk assessment, so we have to assess the risk, okay, in the case of dike flooding. Risk assessment within the theoretical framework of decision analysis can help us in deciding on the optimal dike height by weighing the benefits of reduced dike flooding risk with the cost of increasing the dike height. So how the risk assessment can be done in a from the theoretical point of view, decision analysis will help us to at least decide the minimal or optimal dike height. How it is decided? By weighing the benefits of reduced dike flooding along with the cost of increasing the dike height. So however, a prerequisite for the risk assessment is that prerequisite for the risk assessment means for assessing the probability of dike flooding are established, and this in turn requires that a probabilistic method probabilistic model for the future water level is also available at the same time. Next, uncertainties in engineering problems. So for the purpose of discussing the phenomenon uncertainty in more detail, let us initially assume that the universe is deterministic and that our knowledge about the universe is perfect. So we have to assume that the universe is deterministic and our knowledge about the universe is perfect. So this implies that it is possible by means of an example, that is a set of exact equation systems and known boundary conditions, by means of analysis to achieve perfect knowledge about any state, quantity or characteristic which otherwise cannot be directly observed or has yet not taken place. So when we assume that the universe is deterministic and we have a perfect knowledge about the universe, this sentence or this statement basically implies that a set of exact equation systems and boundary conditions are known, and these boundary conditions are known by the process or by the means of analysis, and this analysis helps in achieving the perfect knowledge about any state, quantity or characteristic of the universe, so which otherwise cannot be directly observed or has not yet taken place. So in principle, following this line of reasoning, the future as well as the past would be known or accessible with certainty. So considering the dike flooding problem again, it would thus be possible to assess the exact number of floods which would occur in a given reference period. So the dike flooding problem can be considered as to assess the risk by taking or assuming the exact number of floods with the previous record which would occur in the given time period. That is the frequency of the floods. In short, the frequency of floods should be determined for a given dike height, and an optimal decision can be achieved by cost-benefit analysis. About cost-benefit analysis, we'll study in our upcoming classes. So whether the universe is deterministic or not, it is a rather deep philosophical question. So despite the obviously challenging aspects of this question, its answer is, however, not a prerequisite for purposes of engineering decision making. The simple reason being that even though the universe would be deterministic, our knowledge about it is still in part highly incomplete or uncertain. So if engineering decision analysis subjects to uncertainties such as quantitative risk analysis and structural reliability analysis. In engineering decision analysis subject to uncertainties, we consider quantitative risk analysis, that is QRA, and structural reliability analysis, that is SRA, which is a commonly accepted view angle is that uncertainty should be interpreted and differentiated in regard to their type and origin. So, the quantitative analysis QRA and SRA can be accepted by a view angle, and this view angle implies that uncertainties are interpreted and also differentiated on the basis of what? On the basis of their type and origin. So in this way, it has become standard to differentiate between uncertainties due to inherent natural variability, model uncertainties, and statistical uncertainties. So by this process or by this way, we can differentiate between uncertainties which occurs due to natural conditions or model uncertainties, and also statistical, that is mathematical uncertainties. Whereas the first mentioned type, that is the natural variability uncertainty, it is often denoted as aleatory or type 1 uncertainty. Natural variability is denoted as aleatory or type 1 uncertainty, and the latter two, that is model uncertainties and statistical uncertainties, are referred as epistemic or type 2. I am repeating, model uncertainties and statistical uncertainties are always or rather referred to as epistemic or type 2 uncertainties. So without further discussion here, it is just stated that in principle, all prevailing types of uncertainties should be taken into account in engineering decision analysis. So when you make a engineering decision or when you have to do an engineering decision analysis, you have to take into consideration these three types of uncertainties, mainly these three types of uncertainties: natural variability, model uncertainties, and statistical uncertainties. In short, type 1 uncertainty and type 2 uncertainty. So this uncertainty should be considered within the framework of Bayesian probability theory. So we have to apply Bayesian probability theory while making an engineering decision based on these three uncertainties. About Bayesian probability theory, we'll study in our upcoming units. Next, we'll again consider the example of Dike. So using the example of Dike, we can imagine that an engineering model might be formulated where future extreme water levels are predicted in terms of a regression of previously observed annual extremes. So the future water level values in case of a dike in an engineering model analysis, it can be done by predicting the regression values of the previously observed annual extreme values. So in this case, the uncertainty due to natural or inherent natural variability would be the uncertainty associated with the annual extreme water level. So here you can relate the inherent natural variability with the annual, that is the yearly extreme water level that takes place. So the model chosen for the annual extreme water level events would itself be introduced as model uncertainties. So the model that you will choose for any annual extreme water level event, it will be certified or it will be introduced as model uncertainties. And the parameters of the model would introduce statistical uncertainties as their estimation would be based on a limited number of observed annual extremes. So finally, the extrapolation, that is mathematically or differentially, of the annual extreme model to extremes over longer periods of time would introduce additional model uncertainties. So when you extrapolate the annual extreme model with that over longer periods of time, this will again result to additional model uncertainties. So the uncertainty associated with the future extreme water level is thus composed as illustrated in figure 1.3. This is your figure 1.3 illustration of uncertainty composition in a typical engineering problem. Whereas the so-called inherent natural variability is often understood as the uncertainty caused by the fact that the universe is not deterministic, it may also be interpreted simply as the uncertainty which cannot be reduced by means of collection of additional information. So, the natural variability which we have already discussed, it is often understood as the type of uncertainty which is caused by the only fact that the universe is not deterministic. And it can also be interpreted simply or in simple words as the uncertainty which cannot be reduced by means of the collection of, we cannot reduce this uncertainty by collecting any additional information or data. So it is seen that this definition implies that the amount of uncertainty due to inherent natural variability depends on the models applied in the formulation of the engineering problem. So uncertainty amount due to natural conditions, it depends on the formulation models that we took earlier. As I have explained earlier, the uncertainty models for formulation of the engineering problem will be considered as the amount of uncertainty for natural variability problems. So presuming or assuming that a refinement of models corresponds to looking more detail at the problem at hand, one could say that the uncertainty structure influencing a problem is scale dependent. So here in this figure, as you can see, figure 1.3, it is an illustration of uncertainty composition in a typical engineering problem. So, okay. The first one, that is the type 1, aleatory uncertainty, that is natural variability uncertainty. In this type, you'll see the first will observe the annual extreme water values as mentioned. After observing the annual extreme water levels, we'll see the model for annual extremes. Okay, so once we decide the model for annual extremes, we go to do regression model or form regression model to predict the future extremes. Why do we create a regression model? In order to predict the future extreme water level that may occur. So this and after regression model calculation, we'll see the predicted future, which I have already said, predicted future extreme water level will be determined. So this model of annual extreme and regression model of predict future extreme comes under type 2 uncertainty, which is epistemic uncertainty. This diagram is important. So, having formulated a model for the prediction of future extreme water levels, as mentioned in the diagram, and taking into account the various prevailing types of uncertainties, that is the type of uncertainty which may occur, the probability of flooding within a given reference period can be assessed. So, how long or how much level will the flood take place will be assessed, or it can be assessed. And just as in the case of a deterministic and perfectly known universe, a decision can be made on the optimum Dike height based on a cost benefit assessment. So this universally decision that we have to take based on the optimum dike height, the minimum dike height that has to be given for a dike, flood dike, it will be based on a cost benefit assessment. It is interesting to notice that a type of uncertainty associated with the state of knowledge has a time dependency. Time dependency is a very important factor in case of uncertainties. So following figure 1.4, this is your figure 1.4 illustration of the time dependence of knowledge. Following figure 1.4, it is possible to observe an uncertain phenomenon when it has occurred. In principle, if the observation is perfect without any errors, the knowledge about the phenomenon is perfect. So observation without any errors, so that phenomenon is considered to be perfect. The modeling of the same phenomenon in the future, however, is uncertain as this involves models subject to natural variability, model uncertainty, and statistical uncertainty. Sorry. So this perfect phenomenon may not be perfect in the later or in the future stages because of the two types of uncertainties that we have already studied, alliatory uncertainty and epistemic uncertainty. So often, but not always, the models available to tend to lose their precision rather fast, so that phenomenon lying just a few days or weeks ahead can be predicted only with significant uncertainty. So an extreme example of this concerns the prediction of the weather. Here you can see the weather prediction. It is given as an example for illustration of time dependence of knowledge. In the past time, the future time, and the present time. Time scale and knowledge scale. Observation may be 100% in the past, but in the future, the prediction may not be 100% because the model may change, the precision may change. That is, as you can see, tend to lose their precision rather fast. And this precision gets lost within just a few days or weeks, depending upon the situation. So the above discussion shows another interesting effect, namely that the uncertainty associated with a model concerning the future transforms from a mixture of alliatory and epistemic uncertainty to a purely epistemic uncertainty when the model phenomenon is observed. So this transition of the type of uncertainty has a significant importance because it facilitates that the uncertainty is reduced by utilization of observations that is known as updating. So this is all for this lecture. Now you can give your attendance now in the chat box. Thank you. Those who have given their attendance can leave. Thank you.